In this lesson, we're going to be looking at how images are stored in binary. So how do we take a photo that maybe you see on the screen or on Google, or whatever happens to be, how do we take that image and turn it into a set of ones and zeros so it can be understood by a computer? In order to really get started, there's a kind of a term you need to be fully aware of. You might already know about it. And what is a pixel? So a pixel is how images are made up on the screen. So if you took a magnifying glass to your screen and looked really carefully, you'll see that every single picture, the screen itself, is made up of tiny little dots. Each dot is will have a color, and all those dots together will make up the image. So a pixel is one of those single squares of color in an image. So we need to understand how images are represented on a computer, understand the term metadata, and understand color depth and resolution and on the file size of an image. So what happens when you zoom in on an image on your computer screen? So if you take a picture you download off the internet and just zoom in and zoom in and zoom in and keep zooming in, what happens to that picture? So here's a beautiful panda that I have downloaded. This is just kind of at 100%. I'm now going to zoom in on 200%, so you can't really tell much at the moment, so it's just obviously a bit bigger, but that's about it. 400%, you could start to see those tiny little squares start to appear. And I'm now zoomed in at 800%. You can see that the squares are a bit more pronounced now. And one of the downsides of using PowerPoint to do this is that it will actually start to blur them slightly as well. Just what it does. And now at 1600%, you can really start to make out the individual. So as I've already said, computer images are made up of tiny dots called pixels. Okay, in the image on the screen, you can see that we have the original image which has been zoomed in, and on that bit you can start to see the pixels, and if we zoom really far in there, you can see the individual squares of color here. So the color of each pixel is represented by binary code. Okay, so each pixel is will have an individual color, and then we store that color as a set of ones and zeros. So the number of colors available in each image, it will depend on the number of bits that we use. Okay, so the more bits we have, the more colors we'll have available to play around with. There are two ways to store image data. The first one is using color maps, which we're going to look at right now, and the second is using RGBA values for each pixels. The second way is how most images are stored nowadays, because most pictures will be stored using 16 million different possible colors. However, there are still some images which are stored and saved using color maps. For example, the graphics interchange format, GIFs, will tend to use that format. So we tend to focus on the first format in the exam. However, it's probably worthwhile knowing the second one as well. Let's start off with a 1-bit pixel. Okay, so if I have a single bit which represents every single pixel, then I only have two possible values. Okay, so it can either be a 0 or it can be a 1. Now what I can do is, if it's a 0, I can represent it as maybe a white pixel. If it's a 1, I can maybe represent it as black. So I have two possible values it can be. So maybe I'm just going to draw an arrow onto that one. So we've got two possible values it can be. So this kind of smiley face is represented by the bit pattern on the left hand side. Now if I start to increase the color depth, then I'll have more colors to play around with. Now the idea of color depth is essentially the same as the number of bits I'm going to use. So the more bits, the more colors I have, and the higher the color depth. So a 2-bit color depth means that I am using 2 bits to represent each pixel. Because I have 2 bits, there are 4 possibilities it can be. It can be 0, 0. It can be 0, 1. It can be 1, 0. Or it can be 1, 1. Okay, so there's 4 possibilities for color depth of 2. If I had 4 bits, then I would get 16 different colors, and there's a little formula you can work out, which is 2 to the power of 2 for 2 bits, or 2 to the power of 4 for 4 bits. If I had 16-bit color depth, it'll be 2 to the power of 16, and this kind of general form, the 2 to the power of n, will work out color depths, the number of colors available for each color depth, to any number of pixels you can think of. So long and short of it, you can have more shades and colors simply by increasing the color depth for each pixel, but it obviously conversely will increase the file size of the image as well. So let's actually see this in practice. So if I have a 2-bit image, remember I said you can have 4 possible colors. Okay, and again on the side here, I have got those represented. Now the colors themselves, what those bit patterns represent, could be anything. You can change that, and essentially each of these binary values, that 0, 0, kind of maps to a color, and the color map is simply saying, given a binary pattern, what is the color it's going to be. So in this example, 0, 0 is white. However, we could easily change that color map to be any color we want to. So we can have it as 0, 0 as maybe pink or purple or any color you want to. So in this example, I've got 1, 0 representing red, and if I kind of bring that over here, sorry, it's getting a little bit messy now. 1, 0 is representing red in my color map. So for a 2-bit image, I have 4 possible colors, and then I write out all the different possibilities and map those to different colors. Okay, and that's how we store the information that we need to. So you're about to see a video of me looking at the following website, 101computing.net. There's a brilliant interactive section called Color Depth. I do advise you to actually go onto this website and have a little play with it to actually see the impact of having different color depths and what happens when you actually try and draw a very, very simple picture to the actual binary code. So this is the 101 Computing website. It's an absolutely excellent resource. So I do encourage you to have a little look around at some of the other things that are on this website. Anyway, the thing we're going to be looking at is an interactive tool, which is under the Understanding Bitmap Pictures. And if I scroll down, you'll find it. So this allows us to kind of create pictures with different color depths. So here I've got a color depth of 1 bit per pixel, which gives me a maximum of 2 colors. So in this case, black and white. And I can draw a picture using that. Underneath, you can see the binary code for that. Because I'm only use 1 single bit per pixel, you can see there's only 1 bit, which corresponds to each of these. Now, if I upgrade to 2 bits per pixel, now notice I've now got 4 possible different colors. And now I can choose one of these colors, and I can, again, draw an image using it. But as I do that, hopefully, you can see down here the binary is again changing. Because I'm using 2 bits, each pixel is representing 2 bits on each line. So on the second line, where I've got a black square followed by red square, you can see I've got 0, 0, which responds to this black. And then I've got 1, 0, which responds to the red. If I go to 4 bits per pixel, you can see I've got a much larger palette now. So again, I can draw an image. You can see each of these has a different binary pattern, which represents each color. And again, you can see the binary changing down here. And because I've got 4 bits per pixel, each bit is represented by each pixel is represented by 4 bits. So there's 4 bits there, then another 4 bits, and so on and so forth. So as I increase the color depth, I'm increasing the number of colors that are able to be shown. So now's a good time to pause the video and actually make some notes. If you've got a textbook, open up the section on images, have a little read through that first before actually doing your notes. But to begin with, describe how images are represented on a computer. Do talk about the idea of what a pixel is and the idea that images are made up of pixels. Talk about the idea that a pixel is represented by a number of bits. The more bits we have, the more colors we can represent, and that is referred to as color depth. So the number of bits per pixel and color depth are the same thing effectively. And then show how the colors are actually mapped to these pixel patterns using color map. Okay. Big tip I would have is go onto the 101 Computing website, draw yourself a little picture using maybe the 4-bit image, and then put that into your notes, and you can maybe annotate it and explain what's going on. So I've got a very simple short program which will allow you to change the number of colors in an image. Now, because you may not have Python or the required libraries for the program that I've created, what I have done is I've shown how this program works and shown how you can use it to reduce the number of colors. Okay, what I really want you to get from this is to see the difference of having a high color count and a low color count. So a high color depth and a low color depth. So this is a very simple program which I can use to change the number of colors in a picture. So I'm going to run the program initially, and what it does is open up a picture, displays on the screen, and it's now using 256 colors. So as you can see, there's a wonderful, beautiful picture on the screen right now, and that is using 256 colors. So I'm going to close this program down. And I'm going to change the color depth. So let's kind of delve into the code a little bit more. So here I've got my libraries. So I'm using a library called Pillow, as well as something called tkinter. So I've got the name of a picture, and I've got the color depth that I'm going to be using, also the color counts. So I'm going to change that to be 64. So I'm dramatically reducing the number of colors. It's then going to open the picture up, convert it, and then display it on the screen. So I'm going to run this again, and you should see a difference now. Okay, so the picture is using a lot fewer colors, and you can start to see there's kind of color banding on my forehead and things like that. So I'm going to change the color depth as well. So I apologize if some of you get nightmares after seeing this start to happen. So here we go. Now you can see at 32 colors. There's far fewer colors to go around, so you can see the colors have now been spread around a lot more. So let's change it to be maybe 16. So I'm just going to run it again. And again, you can see a big difference now. So we've gone from 256 colors down to 16. I'm going to do it one more time, and again I'm going to apologize if this gives you nightmares. I'm going to set it to be 4 colors, and when I run this you'll see a massive big difference, and you can see there's hardly any kind of detail there whatsoever. So this just really shows the impact of having color depth in a picture. So the more colors you have available, the better the quality of the image is going to be, especially photo style images. And if I start reducing the color depth, then obviously that's going to reduce the quality of the image overall. So we've looked at a specific color model already, where we have some bits which represent each pixel, the color depth. The bigger the color depth, the more colors we have, and the idea that different patterns of bits, or ones and zeros, will give us different colors, and that kind of mapping is done through a color map. What we're going to look at now is the RGB model, R standing for red, G standing for green, and B standing for blue. Now, if we have different combinations or different kind of amounts of red, green, and blue, we can get any other color that you can think of. Okay, so for example, we've got this lovely kind of shade of blue, which is made up of 156 reds, 177 green, and 211 blue. Now you're probably wondering what on earth those numbers mean. Well, essentially they're the amount of red, the amount of green, the amount of blue, and it's a number which ranges between 0 and 255. Okay, so again, this kind of shade of pink is going to be mostly red, followed by a high amount of green and blue. So the higher those numbers, the more of that color there's going to be. So if I wanted just pure red, I'd have maybe 255 in the red, then 00 for green and blue. Now, I'll show you on the next slide what that kind of looks at using Genie's color picker, so you get kind of an idea of how you can get every color. But before we get on to that, why do you think we have numbers between 0 and 255? I want you to have a think about that. And to give you a little hint, it's to do with a single byte, so 8 bits. The answer is that the biggest number you can store using 8 bits is 255. So a pixel, which is made up of red, green and blue, is made up of 3 bytes, 1 byte for the red, 1 byte for the green, 1 byte for blue, which is why we use the numbers 0 to 255 for each red, green, blue. So let's actually see how different combinations of red, green, blue can give you different colors. So if you have Genie open, you can click on color picker, color chooser, or if you go onto Google and type in color picker or color chooser, you'll get that in Google as well. Okay, so you can find it in many different places. Anyway, so here I've got red, green, and blue. I can see at the moment it's 255 on all three of them, which gives me a white. Now I'm just going to go around and pick a different color. So let's see, I'm going to go for maybe a yellow, like that. Well, that's made up of 238, 255, and 55. Let's try a different color. So maybe let's go for kind of a purpley style color. I don't know, something like that. 182, 80, 151. So different combination of red, green, blue will give us different colors. Okay, and I can pick any color on this wheel. No matter what the color is, it can be made up using these. So it's a little kind of circle. So I'm just going to move that around a little bit. And there we go. So you can see that kind of color, 19, 225, 216. So most graphics card devices nowadays will use 24-bit color depth, okay, which essentially means we're using 8 bits to indicate red, 8 for blue, and 8 for green. So it is estimated that the human eye can see around about 10 million different colors. So on a 24-bit color depth, we can represent 60 million colors, which is more than enough than we need. So there's no point going any higher than that because we're not going to be able to see the difference, not realistically. So the last thing we're going to be kind of looking at is this idea of metadata and also the idea of image resolution. So essentially we're now looking at some of the key terminology of images. So resolution is essentially going to impact the quality of the picture. So the resolution is the density of pixels in an image, and this is how many pixels are within a certain area. We can measure it using dots per inch, or DPI. So the higher the number of dots per inch, so the more dots we can fit into a single inch, the higher the quality, but also the higher the file size. We sometimes also refer to resolution as the number of pixels going across the width and across the height. So the higher resolution, the more pixels in a certain range, the better image quality is going to be. So for example, if I had a resolution of 60 dots per inch, it means that 1 inch square will contain 60 pixels going across on the left, going across, and then 60 pixels going down, or 60 pixels high. So that would mean I'd have 3,600 pixels in total. Now, if we increase the color depth for that, we again will get better quality images, but it's going to increase the file size as well, because the more bits I use, the more bits are required for a single pixel, and overall the file size will then increase. So the higher the resolution of image, the more pixels I have in that image itself, the bigger the file size is going to be. So image resolution is one example of metadata. Now this metadata is information that's stored about an image, and it's stored with the image itself. So that extra information is stored alongside the data that we need to actually represent each pixel. So that information might include file formats. So is it a JPEG image, is it a GIF image, or is it a bitmap image? Because the different file formats are stored differently and are read differently as well. The height and the width, well, we must know the width of the image, because when we save a file, it's not saved as kind of like rows per se, it's saved as one big long stream of data. If I kind of just looked at it, you can imagine it like a big tape where all the binary is written on it. So I need to know how many bits do I read in to represent a single row in the image. And the height is required because I need to know how many rows I've got. The color depth is obviously incredibly important because I need to know how many bit I'm representing a single pixel with, because if I increase the color depth, then I might accidentally start reading the next pixel. And obviously the resolution, which gives us dots per inch, and essentially the width and height. So we can also have extra information such as the date and time the image was stored, the location it was created in, the author, when it was last edited, and this information is again stored with the picture. Without this metadata, devices, when they load this picture up, wouldn't be able to display it correctly because it wouldn't know exactly how to represent each pixel. Because images come in different shapes and sizes and color depths and things like that, we must have this information stored. So now's a good time to make some notes on all this. Do explain what's meant by the term resolution, talk about the idea of width and height, but also talk the idea about dots per inch. Give some examples of information that metadata includes. The example do like to talk about metadata, so it might be something you may wish to overlook because of all the detail in images in the image lesson. However, you will need to know exactly what is stored in metadata. So have a good number of examples of the kind of information you have in metadata. And finally, describe the effect that color depth and resolution have on the quality and file size. So the higher the resolution, the higher the file size, the higher the color depth, the higher the file size, and obviously putting those two things together, the higher the file size becomes again. But the higher the file size, the higher the resolution, the higher the color depth, the better the quality of the image is going to be. So again, do go to pages 143, 145 in the book if you're a UAB student. If not, then maybe just read whatever book you have, or maybe go online and read about images there.